So we're going to take a separate video here to talk a little bit about the physical properties and reactivity of carboxylic acids and their derivatives. So specifically where I'd like to start is just talking a little bit about the structure of the carbonyl functionality. So once again, we have a carbon that is doubly bonded to an oxygen, and then there's some stuff on the sides. We'll just do that, depending on what sort of structure you have. The important thing here is to note that we've got an sp2 hybridized carbon. So we have bond angles of 120 degrees. This thing is trigonal planar, so it's flat, right? And that's going to affect how this thing is going to react with other molecules. So carboxylic acids, esters, and amides, so specifically esters and amides are derivatives of carboxylic acids, but these three I'd like to draw some important resonance contributing structures, right? So, or we should say contributing resonance structures. In other words, for a carboxylic acid, we would have rest of molecule here, the carbonyl functionality, and then we have this hydroxyl group. So if I put in the lone pairs of electrons on the oxygen, we can delocalize these electrons up into the carbonyl and come out with a resonance structure where we have a double bond over here positive charge on this oxygen, and then we've put an extra lone pair up here on this oxygen and it's got a negative charge. Overall, the net charge is 0. So we have two contributing resonance structures for a carboxylic acid. The same thing can be done for an ester. So I can delocalize electrons. I'll just put a little prime here to say this doesn't have to be the same R group, but maybe it is. Delocalize electrons up into the carbonyl. Remember, we have polarity about this carbonyl, right? Oxygen is more electronegative than carbon, so it's pulling on the electron density in that double bond. So again, we can put the extra lone pair up on this oxygen, put a double bond to this oxygen, a little positive charge here. So we have two contributing resonance structures for esters. For amides, this becomes really important because nitrogen is less electronegative than oxygen. So that positive charge will be better supported, meaning amides kind of, now I guess I can just draw hydrogens here, but you know, these can be R groups too. This carbon-nitrogen bond behaves a little bit more like a double bond than in a carboxylic acid or an ester. The nitrogen, being less electronegative than the oxygen, is better able to support the positive charge. So this resonance structure on the right for the amide is just a little bit more, we'd say, contributing or just a little bit more important than it would be for a carboxylic acid or an ester. So in other words, the resonance structure on the right there for the amide makes a greater contribution than in the carboxylic acid or the ester because it's more stable. The nitrogen is less electronegative than the oxygen, and so it's better able to support the positive charge. What does that mean physically? Well, it probably means specifically talking about, say, boiling points. And all this goes back to intermolecular forces. Amides are going to have much higher boiling points than carboxylic acids. Those are going to have much higher boiling points than esters. Which are going to be probably on par with acyl chlorides. So now we're not talking about reactivity here, we're just talking physical properties, and we're describing, in a sense, the intermolecular forces of attraction. These will probably be on par with ketones. And last will be aldehydes. So they'll all be kind of close, and it kind of just depends on the structure. But specifically talking about the amides here, due to that resonance structure on the right over there, so if we're looking specifically at this structure here, being a greater resonance contributor, because the nitrogen is better able to support the positive charge, that carbon-nitrogen bond behaves a little bit more like a double bond. And so, in other words, the dipole-dipole forces, or the dipole-dipole interactions that you have in all of these molecules, they're going to be a little bit more significant in the amide because that resonance structure is just a little bit more contributing. So, in other words, we have very strong or stronger than a carboxylic acid or an ester, stronger dipole-dipole interactions. Now, in Gen Chem, we talk about the strength of the intermolecular forces of attraction, and we say that dispersion forces are the weakest. Ion dipole interactions are the strongest. But if you're talking just dispersion forces, dipole-dipole interactions, and hydrogen bonding, we typically say that the hydrogen bonding is the strongest of those three. But it kind of depends on the structure, doesn't it? The mass affects the dispersion forces. If you have more polarizable electrons, then yeah, those are going to be more significant, even though they are the weakest intermolecular force of attraction. And the dipole-dipole interactions are kind of like in the middle, right, between hydrogen bonding and dispersion forces. But again, if you have a greater resonance contributor like you have here with the amide, then those dipole-dipole forces become a little bit more significant than say the hydrogen bonding or the dipole-dipole interactions that would occur in a carboxylic acid. So when we're comparing them and their physical properties that are affected by these intermolecular forces of attraction, we have to think about all that stuff, right? You can have dispersion forces that outweigh hydrogen bonding if you have plenty more polarizable electrons. You can have dipole-dipole interactions that outweigh hydrogen bonding in another molecule if, for example, you have a resonance structure that's just a little bit more contributing. So let's pause for a second and just discuss again the significance of the resonance hybrid in general. So somewhere in between those two structures, there's a hybrid, right? And we would draw dotted lines to show the movement of those electrons. And the hybrid kind of better describes the data that we have that corresponds to analysis of the molecule, bond energy, bond length, strength, all that kind of stuff, right? People sometimes have a hard time with resonance hybrids because they believe that it doesn't, they don't really quite understand how you can have two structures that both contribute to an overall, say, hybrid or overall molecule. And I think one pretty easy thing to think about is if somebody were to ask you, if you've never ever seen, this is going to sound silly, but if you've never seen a nectarine before, right, and somebody is asked to describe to you what a nectarine is, and they put it in your hand and you feel it and it's smooth, and they tell you that it's smooth like a plum, And then they tell you to take a bite and you say, but it doesn't taste like a plum, it tastes like a peach. But it's not a plum and it's not a peach, it's a nectarine. That's the resonance hybrid. If that makes any if that makes any more sense. So sometimes people have trouble with these two structures. And when we say in chemistry, this is a more contributing resonance structure, it means we're looking at the product that fell out of some reaction. And we say, of the two resonance structures, this one has a bigger contribution to forming whatever that product was. Or, you know, when we're looking at intermolecular forces of attraction and the physical properties that are affected by it, amides have higher boiling points than carboxylic acids, probably because one of these resonance structures is just a little more contributing than the other. You know, maybe you've got kind of like a fuzzy nectarine or something like that, right? It's just a little slanted to one side. So what I can do, specifically talking about the amides and the carboxylic acids, because those of the three that I've just described are going to have two of the higher boiling points. We can draw, so, you know, you can have hydrogen bonding if you've got hydrogens attached to the nitrogen. If there are groups, then the amide's not going to hydrogen bond to itself. But with those charges being separated on the greater contributing resonance structure for the amide, those are going to contribute more significantly, right, to those dipole-dipole interactions in the overall structure or the hybrid. Additionally, again, if the nitrogen is bonded to one or two hydrogens, they can hydrogen bond with themselves. So amides are going to have, in general, greater intermolecular forces of attraction than carboxylic acids. With a carboxylic acid, each molecule has two groups that can hydrogen bond, and there are dipole-dipole interactions, but since the oxygen is more electronegative than nitrogen, the hydrogen bonding in amides is going to be stronger. So for example, I can draw the intermolecular forces of attraction between, say, carboxylic acid and I'm going to just exaggerate these bonds a little bit so that we can sort of line them up and be able to visualize this a little bit better. Try to get this as lined up as possible for you. So we have lone pairs of electrons on the oxygen. Now remember, there's polarity, right, in that carbonyl. The oxygen's more electronegative than the carbon. So it's pulling on electron density, putting a partial negative charge on the oxygen. And on the other carboxylic acid, we see a hydrogen attached to an oxygen, which has a partial positive charge because hydrogen is less electronegative than oxygen. So these are going to be our hydrogen bonds. They're not covalent bonds, they're just intermolecular forces of attraction. We could have dipole-dipole interactions between the two carbonyls. But there's no actual formal charge. So I'll just, I guess, do this. There's no actual formal charge on the carbon or the oxygen. It's literally just a partial positive charge on the carbon and a partial negative charge on the oxygen. I'll just do this to keep it out of the way. So I'm going to put those charges in so you can see what I'm talking about. The partial positive here, there's a partial negative here, partial positive here, partial negative there, right? We have a dipole moment there. And so there's going to be an attractive force here. So this is a dipole-dipole interaction. In the amide, though, if I draw out the resonance contributor on the right there, so again, nitrogen being less electronegative than oxygen, better able to support the positive charge, that particular resonance contributor is just a little bit more significant to the overall hybrid. So in other words, when we draw out the structure and we're trying to make sense out of the intermolecular forces of attraction, I'm going to choose that resonance contributor. In other words, I'm going to put the double bond on the nitrogen so that I can look at the dipole interactions between two amide molecules. So remember, when we put the double bond between the carbon and the nitrogen, we have positive charge on the nitrogen, negative charge on the oxygen. So now I'm going to draw another one of these sort of upside down underneath. Now, instead of a partial negative and a partial positive charge, I have an actual positive charge and an actual negative charge. So the dipole-dipole interactions are going to be a little bit more significant between these two than they would in the carboxylic acid. Meaning they're just a little bit stronger. So I've got a dipole-dipole interaction here, a dipole-dipole interaction here, but it's between an actual formal positive charge and a formal negative charge instead of a partial positive charge and a partial negative charge. So this is going to be a stronger dipole force. And of course, if the nitrogen also has hydrogens attached to it instead of R groups, then they can hydrogen bond with each other. So overall, the amide is going to have stronger intermolecular forces of attraction. So when we get into their reactivity of these compounds, some of these resonance structures are going to come into play in describing, you know, why are amides less reactive than carboxylic acids? Why are acyl chlorides the most reactive of all the carboxylic acid derivatives? Like why, so we're going to come back to these structures and properties. So how do these derivatives, these carboxylic acids and their derivatives react? So let's have a separate category for that. So how carboxylic acids and their derivatives my cat is hoping to contribute here. So how do these things react? Again, we have our carbonyl. We can draw in our partial charge. So I'm going to put a little Z here because this could be a lot of things, right? So with carboxylic acids and their derivatives, we're talking Z is going to be a leaving group or a potential leaving group. Again, the oxygen being more electronegative, there'll be a partial negative charge as it's yanking on the electron density in the double bond. There's a partial positive charge on the carbon. And so there's a polarity. So we can list all the things we know here. And the way this is going to react is going to be due to the polarity of the carbonyl group. So the spot on that molecule that's likely to get attacked by a nucleophile is going to be that electrophilic carbon. So this right here is going to be where it's at when we attack these molecules. The carbonyl carbon that I've just highlighted is electron deficient, so that's going to be our electrophilic site. It's going to react with a nucleophile. When a nucleophile attacks the carbonyl carbon, the weakest bond, so you've got this double bond here, between the carbon and the oxygen. When that carbon gets attacked, the weakest bond, in other words, you know from Gen Chem that a double bond is made up of a sigma and a pi bond. We remember that the sigma bond comes from the overlap of two hybrid orbitals. So it's got a longer, fatter lobe. Better orbital overlap means stronger bond. So the sigma bond is going to be stronger than the pi bond. So the pi bond comes from two unhybridized p orbitals that have to overlap sort of like across, perpendicular to the internuclear axis. So the overlap is not as great. Maybe just the tips of the orbitals are coming into contact, right? So in other words, the pi bond is going to be the weaker of the two. So when that carbon gets attacked, it's the pi bond, we believe, that breaks. And a tetrahedral intermediate is going to be formed. So when your carbonyl carbon is attacked by a nucleophile, and I'll just put NU, the pi bond breaks. So in other words, we're going to put those electrons on the oxygen, and a tetrahedral intermediate. There'll be a pattern to this reactivity too that you'll notice time and again. And I'll outline it just maybe once when we get into reacting these things. And then you'll notice the same pattern happens over and over. We attack the carbonyl carbon, electron density is put up onto the oxygen. When you break the pi bond, a tetrahedral intermediate is formed. So in other words, the carbon of the carbonyl will go from sp2 hybridization to sp3. So that's something to keep in mind. Just for a moment, when you form that tetrahedral intermediate, your carbon is going from sp2 to sp3. Remember what that means. We have an sp2 carbon, it has 3 electron domains. It's trigonal planar, so it's flat. We form a tetrahedral intermediate, and just for a moment, your carbon goes from sp2 to sp3. All of a sudden, we have a tetrahedron, right? The electron geometry is tetrahedral. There are 4 electron domains after the nucleophile attacks. The tetrahedral intermediate is not necessarily stable, so the pi bond actually reforms and a group leaves. So with the carboxylic acids and their derivatives, it's usually Z, this thing over here. Not always an awesome leaving group, but the more awesome it is, the more reactive the molecule will be. So in other words, if Z is a chloride, right, chloride is going to leave, that's a pretty weak base. It's not even basic. It's kind of neutral, right? So if you have an acyl chloride, when the pi bond forms again, because the tetrahedral intermediate is not necessarily stable, we get that carbon oxygen double bond back. Something's got to go because you can't have 10 electrons around carbon. So if Z is going to be a nice weak base, it's taking off. If your nucleophile is a weaker base than Z, then it will leave and you don't have a reaction, right? So that's another thing that you want to kind of keep in mind. When the pi bond reforms, your leaving group leaves if it's not too basic, meaning if it's not more basic than the nucleophile that attacked it. If your nucleophile is a weaker base than the leaving group, in this case, Z would be our leaving group, so if the nucleophile is a weaker base than the leaving group, then the nucleophile will take off again, and then no new product will be formed, and you'll be staring at starting materials. You won't have a reaction happen. If the leaving group is a weaker base or has been protonated to form a weaker base, so in other words, say we took the hydroxyl group of a carboxylic acid and protonated it to make water, that's a pretty weak base. That can leave, right? Then your leaving group will leave. So this reaction is called a nucleophilic acyl, because we have an acyl group there, R, and then the carbonyl. These undergo nucleophilic acyl substitution reactions. Those are the characteristic reactions of carboxylic acids and their derivatives. So we talked about substitution reactions before, right? With alkyl halides, we can do an SN2 or an SN1 reaction, right? Where you're substituting a leaving group on a carbon, right, with some nucleophile. In these reactions, we're hitting the carbonyl, right, of a carboxylic acid or one of their derivatives, and you're with a nucleophile. So we have a nucleophilic acyl substitution reaction. I'm making kind of a big deal out of the name of this reaction because when we move on to aldehydes and ketones, those fall under the other category of carbonyl compounds where Z is not a leaving group and you can't make it be a leaving group. Those will not undergo nucleophilic acyl substitution reactions. They will undergo nucleophilic acyl addition reactions. It is a different type of reaction. So what am I talking about? Here, let's draw just a general sort of carboxylic acid derivative. So I'll use Z just to keep it consistent. That's going to be your leaving group. Your generic nucleophile is going to come in and it's going to attack the electrophilic carbon of the carbonyl. The pi bond is weaker than the sigma bond, so that will break. And we get our tetrahedral intermediate. We've gone from an sp2 hybridized carbon to an sp3 hybridized carbon just for a moment. And you formed a new bond there between the nucleophile and the carbon of the carbonyl. So this thing is not particularly stable. The pi bond is going to form again. And if Z is sufficiently weak as a base, it will take off. If not, if the nucleophile is weaker as a base than whatever Z was, the nucleophile will take off and you're back at your starting materials, right? But if this happens, you have your carbonyl back again. Right? So this will be, that's your leaving group, your weak base. If Z was something like a hydroxyl group or an alkoxy group, like with an ester, you would, or an amide, right? Those are stronger bases, right? The amide anion is a pretty strong base, so it's not going to be leaving without some help. You can protonate it, turn it into ammonia, that'll take off, right? Or you could take the hydroxyl group, protonate it, make water, that'll take off. Or you could take an alkoxy group and protonate it and the alcohol will take off. But really of these derivatives, the one Z group that doesn't need any help will be the halide. So an acyl chloride is going to be our most reactive carboxylic acid derivative because the chloride anion isn't even basic. It's pretty neutral. It's like a spectator ion. So that's going to take off. Again, these molecules are going to undergo nucleophilic acyl substitution reactions if the nucleophile is more basic than the leaving group. And the relative reactivities for these, just based on the leaving group's, the weakness, right, of the basicity in the leaving group. So relative, and I say relative because it kind of depends on what the rest of the structure is, right? So relative reactivities of these compounds. So who's the most reactive, who's the least reactive, in other words. We have to consider two steps to these nucleophilic acyl substitution reactions. When you're deciding who's going to be the most reactive, who's going to be the least reactive, the first thing that's going to happen is your nucleophile attacks. It's going to attack the carbonyl carbon to form your tetrahedral intermediate. I'll just abbreviate this. The second thing that's going to happen is your tetrahedral intermediate is going to collapse, form the pi bond again. So tetrahedral intermediate. In other words, your leaving group will leave. So if the carbon of the carbonyl is more electropositive, in other words, it has a greater partial positive charge, and you have a nice basic or neutral but small nucleophile, right? Something with a lone pair of electrons, you will get the carbonyl carbon attacked by the nucleophile, form the tetrahedral intermediate. The tetrahedral intermediate will then collapse and the leaving group will take off. The weaker the basicity of the leaving group, the easier it is for both steps to occur. So in other words, we can judge the reactivity of these particular carboxylic acids and their derivatives by the basicity, comparing the basicities of the leaving groups. The acyl chloride, the leaving group would be chloride, right? And that is not even basic. So it's weaker than an alkoxide, which is pretty on par with a hydroxide. And those are going to be weaker than the amide anion. So therefore, in terms of who's the weaker base, this is the weakest. This is going to be the strongest. These are all the leaving groups if we attack these things, right? The weaker, again, the basicity of the leaving group, the easier it is for both of those two steps that have to happen in this reaction to occur. So in other words, we can say that since the weakest base is the chloride anion, the acyl chloride will react the fastest. And the amides, we'll just use hydrogens here, but they can be R groups. Will react the slowest. So In the next video, I'm going to elaborate on the reactions of these particular compounds, and I'm going to break them into those categories: acyl chlorides, esters, carboxylic acids, and amides. I would like to discuss them in order of their reactivity. So in this order, starting with the acyl chloride, we'll talk about characteristic reactions of those particular compounds. And then we'll jump into esters, carboxylic acids, and amides. You will notice a pattern to their reactivity. It will apply pretty much across the board. And it will also apply again when we start talking about aldehydes and ketones, although in those particular cases, you don't have a leaving group. Z will not be able to take off because it'll be an R group or a hydrogen, right? So either hydride leaves or some carbanion leaves, and that's not likely to happen, right? Because those are wildly basic species. So starting with acyl chlorides, we'll do a few reactions. We'll jump into esters, which will take a little bit of time. And that's where we're really going to notice a few intermediates in between. We've got protonated intermediates, neutral intermediates. I really want to talk a little bit about the stability of those because a lot of these reactions are going to be reversible. And so we have to just lean back a little bit on some of our general chemistry equilibrium knowledge when we start talking about how to encourage the formation of product when at equilibrium, two possible products are equally stable. What can we do, right? So we'll bring Le Chatelier's principle back in, equilibrium stuff, all that in the next video.